So before the midterm, we were looking at mechanical forces and mechanical energy, the kinetic and potential energy and all of that. If you remember, we used equations such as F equal ma, where F is the force, m is the mass, and a is acceleration to determine the force. And then we used equations such as work or energy is equal to the force times the distance. This is work or energy, all right? To determine how much energy is being consumed or provided, depending on the force that is being applied at a specific distance. And then we also looked a little bit about power P, which is simply just, and the power is just energy over a specific amount of time. So it's simply energy or work over time, or you can say it's energy over time, work done or energy over time. Okay. And if you remember, the unit of force was newtons. You remember unit of work or energy was in joules, and the unit of power was in watts, all right, which is joules per second, because you have energy in joules and time in seconds. This is just a quick refresher of what we did before the midterm. Now, when we come to electrical systems, we are going to be using similar concepts to understand how electrical energy is given or dissipated, yani, depending on where it is supplied from and where it is being absorbed in, and we're going to see a bit more about that in a bit. But to start off, I want to start off with just a general reminder, since we already talked about this before, but it is very important to understand the units you are using. Okay, so units is always very important. The type of units we usually use are SI units, meaning for length, we are going to be using meters. For mass, we're going to be using kilograms. For time, we are using seconds. For current, electrical current, which we will talk about in a bit as well, we use something called ampere, which is amperes. All right. And for temperature, we don't deal with that a lot. We use Kelvin. And then there is luminous intensity in candela and the amount of substance, which is mole, which I'm not going to go into. Most importantly are these units, which you will be using a lot of, especially current in amperes, time in seconds. These specifically in electrical, we're going to use a lot. Another thing you guys need to know هو prefixes. The prefixes meaning إذا عندنا مثلا mega joules. All right. What does this mean? This means we are multiplying joules by 1 million, because mega represents 1 million. So, or you can write it as times 10 to the power of 6 joules. All right. So the main ones you guys need to know is mega, which is times 10 to the power of 6, and then a kilo. For example, let's say kilojoules. Let's keep the same idea. So kilojoules will be like joules times 1000, or you can say times 10 to the power of 3 joules. All right, then we see milli. The difference between milli and mega, mega is capital M, uppercase M, والملي بيكون lowercase m. Millijoule, this is dividing by 1000. So it's going to be times 10 to the negative 3 joules. All right, and then we have a few more, which is microjoule. This is dividing by a million, which is equal to times 10 to the minus 6 joules. And then we have nano, which is dividing by a billion, and 1,000,000,000,000, or simply put times 10 to the minus 9 joules. And lastly, which you don't see a lot, but sometimes used, pico, which is J divided by a trillion, which is 12 zeros. Okay, so this is times 10 to the minus 12 joules. All right, these are very important. Knowing your prefixes is very important, because this basically they might give you in a question, or you might see it in a question somewhere. These are the units that might be given for a specific energy in this case, because we're talking about joules. But when you're using in calculations, we need to go back to our standard units in this case, which is joules. All right. So when you're given something in kilojoules, you need to know how to convert it back to joules so that you are solving properly and the numbers are all correct. All right. So this was just a quick refresher. I'm pretty sure most of you already know this. So let's get into electricity. So electricity, what is it basically? Just one moment. Sorry, just a second. So, electricity. What is electricity? Electricity is basically a flow, all right? So let's say we have a long wire like this. I'm just going to make this wire a bit larger, all right? The electricity is basically the flow of electrons, all right? Electrons are negatively charged particles, if you remember. This is just a little bit of theory. You don't need to know this very well. So these are flowing in a specific direction, all right? So when these are flowing at a specific direction due to mechanical properties, due to whatever, due to power being provided, this causes current, all right? This causes a current. زين تيار يعني, all right? This causes a current, and usually the current's direction is in the opposite of where the flow of electrons is happening. So this is going to be the direction of current, okay? This is just the way they have يعني, and they just simplified it this way, and they have just defined it this way, and then the direction of current is always opposite to the flow of electrons. Electrons, if you remember, are just if you have an atom يتذرة يعني, and then if you have an atom, you're gonna have electrons flowing outside here. All right, these are all electrons, okay, which are negatively charged, and then here you have your protons and neutrons, which are positive or no charge at all, which are which are the neutrons. And then this doesn't matter that much. Okay, the idea is I just want you guys to understand, and there's gonna be a flow. Electricity is just a flow, similar to water. When water is moving inside a pipe, or if you're opening a sink يعني في البيت تفتحونه تشوفون ماء قاعد يمر. This is flow. So in case of electricity, it is the exact same thing, and they call that electric current or just simply current. Okay, so current is usually denoted as I. I being current in amperes, which is the unit of current. All right. So again, current is just simply the type of flow that you are having. Now, another thing defined is something called a coulomb, which is charge. All right, a charge. A unit of charge is basically the amount of electricity that is flowing. All right. So, for example, let's say this point, there's this much amount of electricity or amount of current that is flowing at a specific amount of time. All right. This is what they call charge. So, how much charge something has. So, charge is basically current times time. Okay. In other words, this is usually given as Q, which is equal to I times T. All right. Q, the unit for charge is coulombs, C. So this is coulombs, right? The unit for charge. It's equal to the current, which is in amperes, times the time, which is in seconds. All right. Remember, the units have to be in amperes and in seconds for this to be proper, to use this equation properly. And then, الحين, this is simply just an equation you're going to be applying. All right. If we want to look at a very quick example, for example, if there was a question that says current is 5 amperes and it's flowing for 2 minutes, all right? And it says find amount of electricity transferred. And then find the amount of electricity, or electricity, in other words, they mean the charge. And then, so how much charge, how much of this, how many of these electrons are basically moving in this amount of time, in this 2 minutes? Your first step in solving such a thing is, first of all, making sure that your units are all in the standard units. So first thing we notice is our current I is equal to 5 amperes, which is correct. This is the unit that we should be using in standard units. But time is given in 2 minutes. And remember, if you want to convert time to seconds, you're going to have to, if you use the method which I explained previously. So we want to cancel minutes, so we're going to put minutes down. And we want seconds instead, so we're going to put seconds up. 1 minute has 60 seconds in it. So the minutes will cancel, and you're just going to be multiplying 2 by 60 for the seconds. So time is simply 120 seconds. All right. Again, I prefer using this method if you guys still get confused من ناحية التحويلة يعني if you're trying to convert units. But if you guys already can do it directly, you guys can do it directly. Just make sure that you are doing the conversion correctly. And remember, you need to have it in seconds. You cannot just multiply 5 amperes by 2 minutes. That will be incorrect. All right? Because here, the unit for coulomb, it has to be amperes times seconds. All right? So Q is going to be equal to I times T, which is we have our I as 5 amperes, and we have our time as 120 seconds. Put that into the calculator, and you will get 600 coulombs. And that's how easy it is to solve such a question. Notice the difficult part or the trick here is knowing that you have to convert your units, okay? And this is a very important thing you guys need to focus on, all right? And that's pretty much it when it comes to charge. All right, it's just current times time, which is an equation you guys, I'm pretty sure it's going to be provided in the exam, but you just need to make sure you know the units that you're supposed to use so that you can apply it properly. Not an hour. No, you are not going to be doing it an hour when you're trying to find charge. All right, because it's a part of the SI unit. So our SI units, we have length in meter, mass in kilograms, time, it has to be in seconds, and current has to be in amperes. All right, so you have to follow your SI units when you are solving. All right, so now we got a general idea of what electricity is. And then it is the flow of electrons. All right, so we know how to find the amount of electricity that is moving through time. All right, but that is not the only thing that we look at when we are talking about electricity. So if you have, let's use the example of water. All right, so let's say you have a bottle of water. Okay, a bottle of water, something like this. Okay, this is filled with water. And water is, it's open from this end, so water is flowing in this way. All right, so this water is your current. So this water is flowing. This is your current. So let's call this our I, basically, in terms of electricity. Remember, electricity is the same idea as the flow of water, okay? It's the same exact concept. However, we cannot visually see it. So we are using this example to visually be able to see it better. So if you notice here, we have this opening of this size, all right? You're going to notice that flow is going to be something like this, right? So it's going to be flowing in this size, and then however it goes down, it doesn't matter, but this is our current going downwards in that direction. But let's say now we have a much bigger opening. So let's say the opening of this tank, same size, but just the opening is bigger. All right, again, this is water, but now if you notice, the opening is much bigger. Then it's the same height, it's at the same level of height, the water, nothing has changed. It's the same size from inside, nothing has changed. The only difference is the opening has become larger. All right. If you notice now, we have much more current flowing. There is a larger amount of water that is flowing, or in our case, a larger flow of electricity that is flowing. All right. So here, this current, we'll call this I2. Let's call this I1. So you're going to know that I2 is much larger than I1. But what is the thing that changed? So if you notice the opening here, this is what we call resistance. All right, this is ليش يسمونها resistance؟ لأن it's resisting. يعني بما معناه resistance basically means something that is trying to hold something back. زين شيء قاعد يود الشيء ما يخليه يمشي ما يخليه يتحرك. This is what they call resistance. So if you notice here, there's more resistance, a larger amount of resistance, then it's a smaller amount, a smaller space, smaller gap available. So this wall basically is resisting the amount of current that is going to be flowing. So here we have high resistance. All right. So in other words, we call this R1. All right. And here, if you notice, here we have a much bigger opening. So here we have lower resistance. All right. So this is R2. So if you notice in this case, then again, if you are just going to write this down mathematically, R2 هني is much bigger, or I should say much smaller than R1. لأن هني we have a lot more resistance. We have high resistance. إن هني the walls of the container is resisting more current. So the resistance is high. لأن we have it closed. We have it يعني constricted. مترعص المكان. ففي resistance wide في المكان. هني ما عندنا wide resistance لأن تشوفون is there is a small wall only holding it back. There is a larger opening. So we have a much lower resistance. So if you notice, when we have a higher resistance, all right, sorry, a higher resistance, our current is going to be much smaller. And then when resistance is higher, the current is going to be much smaller. And when the resistance is lower, ما في resistance wide, a larger opening, you're allowing more current to flow. All right. So this is the concept of resistance. All right. So resistance R in electricity is the same thing. It's called resistance, and resistance exists in all electric wires and all components and all of in everything. Resistance is there. It just exists everywhere. All right. For resistance, usually the units of this is in ohms, which is given by this symbol. All right. So this is what they call resistance. Okay. So the resistance is basically just how much it is holding back current. However, here we are not considering one important thing. Remember that I said here we have the same height given, right? This height, it's at the same level. So this H, it's at the same level. What if this was at a higher level? Or what if this tank had a force being applied from up that is forcing this to move faster? It will be a completely different case, right? So again, now if we want to look at this, so now we have defined our resistance. Now we have defined our current as well. We know what current is. We know what resistance is. But let's say if we are looking at this from a mechanical point of view, then let's say there's water falling from up here. All right. Let's say that there's water and there's a river. This is a hill. This is a waterfall. And water is just falling down here. Okay. Obviously, if we have a much taller hill, water is going to be going down much faster as it reaches the bottom, right? So يعني, because of gravity, water is going to be flowing much faster in this case. Why? Because here we have a larger height. Here the height H2, for example, and this is, let's call it H1. Okay? So when we're talking about water, we're talking about height, obviously. In electricity, there's the same exact concept where you're going to have something called voltage, or sometimes also known as potential difference. So voltage or potential difference. What does this voltage mean? All right. Mechanically, let's explain it. So when we are saying this height H1, all right, what do we mean by height H1? We mean the height from this ground. All right, so from this ground, this is the ground in this case, and this is the ground in this case. So when we're talking about the height, we're talking about from up here all the way to here. All right, this is our reference ground. This is where what we call zero. Yani this height here is zero at the ground. So H1 is going to be the distance from the top of this cliff, you can call it, all the way to the ground. And H2, similarly, it's the same exact idea. So this is our ground level, which is zero height. And this is your total height. Okay? Here, H2 is much bigger because the difference in height is much larger. In electricity, that is the exact same idea of voltage. Voltage basically responds to current, and the same idea where voltage is basically the force that is pushing the current to move forward. So what do they mean by potential difference and voltage? Potential difference or voltage is simply just the amount of, let me make it simpler. So voltage, all right, is the amount of power you need to put in. All right, so let's say the amount of power so that you can overcome resistance and have current flowing. Okay, so it's power over current, which I will look at later on more into detail. But in simpler terms, it is how much energy you will have to spend so that you can move 1 coulomb of charge. All right, that is basically what voltage is. يعني احنا هني we are depending on gravity, صح? So gravity is the reason that this waterfall over here, it has a much higher potential difference, or a much higher gravitational potential energy at this point. And when it reaches the bottom, it has a lot more of kinetic energy because there's a much larger height. In this case, it is much smaller, and voltage can be thought of in the same way. If we want to use the example of the water bottle, then for voltage. So if we have two water bottles, okay? Two water bottles of the same exact size. Okay, so I'm just going to copy paste this. Yani, in other words, the resistance is the same size. So here we have resistance, remember? This is the resistance resisting the water from falling out. And here we have our current flowing down. Okay? So voltage is basically if you apply a force to this water bottle. يعني إذا عصرتوا على هالwater bottle الحين. يعني if you squeeze the water bottle, إنزين? You're going to be applying a force onto this water for it to escape. And this is exactly what voltage is. Voltage is basically the force that is being applied, or the additional power or energy being provided to the system عشان يحرك الcurrent a bit more, no matter what the resistance is. So in this case, this voltage here is going to cause the current to flow much more. إذا عصرتوا a water bottle, you will see the water will flow much faster than if you just leave it by itself. So here we're going to have a much higher current. This is just the basic concepts of what voltage and current and resistance are compared to a mechanical system, عشان you guys get a better idea to look at it. But let us talk about it in electricity now. So we have defined three things now. We have our current, which is given as I, all right, which is in amperes. We have our resistance, which is our R, which is given in ohms. And we have our voltage, which is V, and the units for it is volts, which is also given as V. All right, so it's volts, which is V. All right, so A, which is amperes, and this symbol is the Greek letter for ohm. Okay, these are the units for these three things. So if you noticed, all of these three things are related, depending on the water bottle example. All of these three things are related. So what is the relation? The relation is basically V, the voltage, or let's start with resistance actually. Resistance is simply equal to, all right, we use red for I, but V first. So voltage over current. Why do we have this relation? Because if you notice, if we can keep everything constant here, and then let's look at the water bottle example. All right. Okay, this is the water bottle. It's actually opened from here. It's not closed. So this is our water bottle. Let's say that the voltage is not being touched. Okay, so we're keeping this as a constant. All right. If this resistance, all right, is increased, if we make this smaller, the current flowing is going to decrease. So if we are increasing resistance, the current is going to decrease, right? Because current at the beginning was flowing very easily, but if we make it smaller, current is going to be much smaller. This is why this relationship exists, because as resistance increases, current decreases. In math, this is known as an inverse proportionality, all right? But if you have the same current, or if you want the same current to flow now, so if we don't want voltage to be constant, now we don't want voltage to the current to change. We want the current to be constant. إنزين؟ يعني نبغى هذا الكرنت ما يتأثر. إذا إحنا we increased resistance, by increasing resistance, we're going to make this smaller, right? We're going to make this a bit smaller. What do we have to do? So if we increase resistance, we're going to have to increase the voltage so that the current will stay the same. So there has to be a force being applied to this water, or energy from outside that needs to be applied to this water, so that the flow is being increased more and more. And this is why this relationship exists. Again, at your level, all you guys need to know is V is equal to IR. All right, this is the equation, or R is equal to V over I. This is the equation that you're going to be using almost every day in your life if you are an electrical engineer, or even in mechanical, even in any engineering. If you see any electrical system, this is the most important equation. This equation is known as Ohm's law. Okay, this equation is also known as Ohm's law. The way you guys can remember this equation is using something that usually people use called the Ohm's triangle. All right, so Ohm's triangle. What is Ohm's triangle? So you're going to have something like this. You're going to have voltage here. You're going to have resistance here, and you're going to have current here. All right. How do you look at this triangle? And this triangle, the idea of it is to know which one you are trying to use depending on what you are trying to find, and we will try to use it in application later. But this is the Ohm's law triangle. What does this mean? This basically means that the same equation. So let's say, for example, we want to find our R, right? So if we find R, we look at V and I. V is at top and I is at the bottom. So we can write it as R is equal to V over I. Okay. Another way of looking at this triangle is, let's look at it from I. So let's say we want to find I. I is V over R from this triangle. V is on top and R is at the bottom. So I is equal to V over R. All right. It's just a way of rearranging the equation easily. That's all it is. Okay. And then now let's look at it from the point of view of V. For V, it is simply just R times I because they're on the same level. So V is equal to R times I, or I times R. Okay. This law is called Ohm's law. This is how you use this triangle just to make sure that you know how to apply it depending on what you try to find. So for example, let's say voltage and current was given. You know you need to find resistance. You know you'll have to use the first equation. If voltage and resistance was given, you need to find current. And if resistance and current is given, you need to find voltage. Okay. And we're going to do a few problems about this as well. But before that, I want to explain one last concept. So the last thing I want to talk about is we talked about resistance, right? Resistance is simply ohms, all right, or R, which is in ohms, okay? So there's another thing called conductance. Conductance. What does that mean? Resistance, مثل ما قلنا, it is something that is holding back something or is stopping something from moving. Conductance in electricity is allowing it to move more. So it is providing more space for it to move, or providing the ability for something to move. This is just simply the inverse of resistance. It is 1 over R, and the unit of it is Siemens, or also used as S. That's all conductance is. Conductance is just simply 1 divided by the resistance. So for example, let's do a question like this on this point عشان نختمها with conductance, because this is a very important thing. Because so far it's very easy. You're just applying equations and just solve, right? But let's start with part A. So part A, the question first of all says, find the conductance of a conductor of resistance this much, and this much. All right. So we have R for the first one is equal to 10 ohms. Simply conductance. Conductance is usually given by the letter G, actually. So let me write this here somewhere. So conductance is given by the value G, which is equal to 1 over R. Okay. So G is 1 divided by R. What is our resistance? It's 10. So this is 0.1 Siemens. All right. Now for the next one, for part B, we have resistance is equal to 5 kilo ohms. Remember, the very first step is making sure that this is in the proper SI notation. In SI notation, when we are using amperes, you notice that ohm has no prefix before it. يعني لازم يكون in ohm. Same thing for voltage, it has to be just volts. And same thing for amperes, which should just be A. All right. So since we have 5 kilo ohms, remember that kilo is simply just 5 times 10 to the 3, or in simpler terms, it's 5 times 1000 ohms. So this is equal to 5000 ohms. So now when we want to find G, it is 1 over 5000. All right. So make sure, this is the trick here. Make sure your units are correct. So this is going to give us 1 over 5000 is going to be 0.0002 Siemens. All right. Or you can just put it as in, wait, let me double check. Yeah. Or you can simplify it and do it as 0.2 milli Siemens. All right. Again, conversion of units, just to explain what I did here. So the way you convert from Siemens to millisiemens is the same exact idea. So 0.0002 Siemens, all right? Just in case, yani the question wants it in millisiemens. So what are we trying to cancel? We're trying to cancel Siemens. What are we trying to put instead? We're trying to put millisiemens, all right? We know that 1 Siemens is 1,000 millisiemens, okay? So we're going to be canceling our S and S. We're going to multiply 0.0002 by 1000. So it is going to give us 0.2 millisiemens. It is very important to understand how you do your unit conversions. All right. Last one, it says 100 milliohms. Part C, it says 100 milliohms. So R is equal to 100 milliohms. Again, this is in milli. Milli basically means 100 times 10 to the negative 3, or it is 100, this is ohms, or it is 100 divided by 1000 ohms, all right? So this is simply equal to 0.1 ohms, okay? So if we want to find our conductance now, it is 1 divided by 0.1, which is simply equal to 10 Siemens, okay? If you noticed here, the most important thing is units. When you're solving question, this is the trick that they're always going to be bringing. It's not about how you apply the equations or anything. It is just about knowing how you can use how to convert your units. Okay, so let us apply Ohm's law. All right, let us see some questions that uses Ohm's law. Before I proceed, yeah, anyway, Ohm's law. Anyone has any questions about this? Because this is basically what we are going to be applying for everything. The idea is we're going to be combining this concept with the energy concept later on to find power, to find all of that. But I want to first make sure you guys understand Ohm's law clearly. We'll do a few questions on that. Then I will look at some questions with power. Is it clear so far? Any questions? Okay, I'm gonna guess that everyone's okay with it. Let's start with an easy one. So the current flowing through a resistor is 0.8 amperes. So we know that I is equal to 0.8 amperes. When a potential difference of 20 volt is applied, remember PD is equal to voltage, all right? So it's equal to 20 volts. You can keep it as PD if you like, but the more common way it's used is voltage. PD, simply this means potential difference. Okay? This is what potential difference is. It is just the voltage that is being applied. Determine the value of the resistance R. So if you go back to our triangle, we are trying to find R. Okay? So if I just copy paste this down one more time, so I show you how we use it. I'm going to just use the triangle one time, so you guys just know how it's being used if it's more easily for you. Okay, so this is our triangle. So we are trying to find R in this case. Okay, so what we are trying to find is R. So we're going to be circling everything that's not R, so we can have an equation in terms of the others. So R is going to be equal to V divided by I. Before that, let us make sure that our units are correct. So we have amperes here, voltage here. Yes, we can use these units. There are no prefixes. It's 20 divided by 0.8, which is equal to 25 ohms. All right? Pretty straightforward, pretty easy question. Just showing the concept. Let's do another question about this. So again, determine the potential difference. So now we need to determine potential difference. This is our unknown. So PD, which is also known as voltage, this is what we need to find, all right? Must be applied to a 2 kilo ohm resistor. معناته our resistor is 2 kilo ohms in order that a current of 10 milliampere needs to flow. So I is equal to 10 milliampere. Now notice here we have kilo, we have milli, we need to convert these back to ohms and ampere. So let's start with this. Kilo basically means times 1000, so 2 times 1000 ohms, which is 2000 ohms. Milli means just times 10 to the negative 3 or divided by 1000, okay? Ampere, this is going to be equal to 0.01. Yes, 0.01 amperes. Now we have the resistance and the current in the correct units. If we want to apply the same triangle again, all right, if we want to apply the same triangle again, what are we trying to find now? We are trying to find voltage. We are trying to find voltage. So voltage is up here. This is voltage. So we are going to be using these two like this. So they're going to be multiplied. So V is equal to I, R times I, or I times R, which is 2000 times 0.01. So our voltage is simply going to be 20 volts. Okay, very straightforward, very basic. Okay, let me try to find one that is a bit more interesting. This is straightforward, similar idea. Okay, let's look at this one. Let me see. Do you guys have any questions so far? No questions? All right. So let's look at this question. Problem 6. A 100-volt battery is connected across a resistor, Zen, and causes a current of 5 milliampere to flow. So what is the voltage we know? The voltage, first voltage given is 100 volts for the battery. So the V battery, we'll call it VB, is equal to 100 volts. The units are correct. That's fine. Connected across a resistor and causes a current of 5 milliamperes to flow. So our current I is equal to 5 milliamperes. Let's directly convert this to amperes. So this is 5 times 10 to the minus 3 amperes. And you can leave it either like this, or if you want, you can write it as 0.0005. No, that's too many zeros, 0.005. All right, amperes. Okay. Now let's see what the question wants. First, it says determine the resistance of the resistor. Easy. So we know using the triangle R is equal to V divided by I, which is 100 divided by 0.005, which simply is 20000 ohms. All right, 20,000 ohms. Or you can write this also as 20 kilo ohms. Just the same way of conversion. We have 20,000, all right? So we're going to be dividing by 1,000 to put the kilo ohms. Same idea for conversion that I did earlier. Let's continue reading the question. If the voltage is now reduced to 25 volts, what will be the new value of the current flowing? Now, remember, this is a resistor. The resistor has a specific resistance that we found, which is 20 kilo ohms, all right? Or 20,000 ohms. So now the new voltage, V new, is equal to 25 volts. And they're asking us to find the new current, I new. Again, we have the resistance, doesn't change. The resistance is a constant value, does not change, all right? So the resistance, what we need to find is current, and using the triangle, I is equal to V divided by R, which is equal to 25 divided by 20,000 ohms, which is going to give us 0.0125 amperes. All right, again, you can convert this into milliamperes. It will be 1.25 milliamperes. And that's pretty much it. So keep in mind, resistance, a resistor does not have the resistance of a resistor does not change, okay? The resistor usually has a constant resistance. Voltage and current may change depending on if you're manipulating the voltage or that, or if you're changing the resistor as a whole, which I will talk about more in a bit when we go into circuits, because I have not started circuits yet, but we will start that today, inshallah. Let me look at any other questions that might be interesting. If you have any questions while I'm solving, please feel free to ask. What is resistance? And then let's look at this one. So here, this question simply says, what is the resistance of a coil which draws a current of 50 milliampere? All right, so part A, I is equal to 50 milliampere, which is 50 times 10 to the negative 3 amperes, which is 0.05 amperes. All right, so the very first step is always going to be converting from milli, from kilo, from micro, from pico, converting that into the standard international units. And it is from a voltage, from a supply of 120 volts. So our supply has 120 volts. Okay. So what do? Again, we need to find the resistance. So for A, R is equal to V over I. Okay. Using the triangle. So it's 120 divided by 0.05, which is going to be equal to 2,400 ohms. For part B, again, it is the same voltage, but the current now is 200 micro. So I is equal to 200 microampere. Remember that micro means 10 to the minus 6 or divided by a million, okay? Amperes, okay? I'm going to leave it in this form. So again, voltage is 120 volts. We apply the same exact equation, V divided by I. This is going to give us 120 divided by 200 times 10 to the negative 6, which is equal to 600,000 ohms, or you can say that this is 600 kilo ohms. Same thing with this one. You can say it's 2.4 kilo ohms. All right. Obviously, with practice, you guys are going to get much better at understanding how to convert the units, understanding what it means to convert units, and all of that very quickly. All right. And that's it. This is how you solve it. Again, the whole trick is understanding how to convert your units, how to identify your prefixes, and all of that. Tamam. Let's do this one. So before I actually go into this question, I want to explain to you guys something from Math 1 that I remember you guys, I'm pretty sure you guys did. So if we had an equation that y is equal to 5 times x, okay? If you wanted to draw this equation on a graph, then if you wanted to draw it on a graph, you're going to take random points and plot them, right? So this is your x graph, this is your y graph. And this is a linear equation. معناتها ما عندنا squared or cubed or anything. So this is a linear equation, so it's a straight line. So let's start with y equals 0. X is going to be also equal to 0. So this is our first point. And then let's say x equal 1, y is going to be equal to 5. Let's make it a bit smaller, so for the scale, so let's say 2x. Okay, so y is equal to 2. X is equal to 2, y will be equal to 4. And so on and so on and so on. So if you want to draw the graph, it's going to look something like this. Let's say this is 1, and this is 2. So this is another point. Let's say this is 2, and this is 4. It's going to be somewhere along here. And if you draw the line, it's going to be a straight line that goes through both these points because you have a linear equation. Okay? So now, what is the slope here? The slope, remember, our general line equation is y is equal to mx plus b, where m is our slope. صح ولا لا? If you remember from math 1, basic draw a linear equation line. So in this case, our slope is 2. This is the slope of our line. So what if we wanted to put, instead of y and x, we are going to put current and voltage. So let's draw a graph. And this is voltage, and this is current. This is in amperes, and this is in volts, right? So what if we put current and voltage like this? So معناته عندنا I is equal to the slope, whatever it is, times the voltage, right? We know that V is equal to R times I. So if this was in the opposite direction, we know that this would be R. But in this case, we have our I times V. But what else do we know? We know that if we rearrange this equation, okay, so that I is by itself, okay, so this is going to become I is equal to V, or let me write it this way, 1 divided by R times V, okay, or V over R simply. All I did was I moved this R and put it under the V. That's all I did. Now we know that this is a very familiar, this is our slope, right? This is our M, this is the slope. But this is also very familiar. We did this earlier. What is this? This is conductance, 1 over R. So we can write that I is going to be equal to the conductance, G, times V. And then we can plot it accordingly depending on that equation, right? So this is the basic idea of it. However, if you want to find resistance from this slope, let's say I just drew this line, all right? Let's call this resistor, R1. Okay, this is a resistor R1. Okay, the slope of it is, yes, it's the conductance. But if I wanted to find the resistance value R, how can I find it? It's very simple. You take any point along this line. Let's say we take this point. Okay, and then we're going to look at the I value for it, and we're going to look at the voltage value for it. So here, let's say that this is 4, and let's say that this is 6, for example. Okay, so what is our equation for resistance? We know that resistance is equal to voltage over current. So what is the voltage that we found? It is 4 divided by what is the current? 6. So we know that this resistor has a resistance of 2 over 3 or 0.67 ohms. Okay, this is how you would use the graph if you were given a graph to find out the resistance, or if you need to find the slope, you know that's just simply 1 divided by the resistance, or if you're given the resistance and you need to find the point for the voltage or whatever, you know how to use this graph now to determine all of this. So now let's look at a question that is using this. So there's this question that says the current voltage relationship, all right? The current voltage relationship for two resistors A and B is as shown. Determine the value of the resistance for each. But keep in mind here, a very important thing to notice is that here, your unit is in milliamperes, all right? And this unit is voltage. The unit here is fine, in volts, I mean. This unit is fine, so it's in volts. But the milliampere, we're going to have to be converting it later on. So we can take any 2 points, all right? Any 2 points along this line. They're for resistor A and resistor B, which are our 2 lines. So let's look at resistor A first. Resistor A, if you notice that these 2 lines are already given for us, this point is taken. So for this point, I is equal to 20 milliamps, and V is equal to also 20, but volts. Remember, this is in milli, so this is 20 times 10 to the negative 3 ampere. How can we find resistance? Resistance R is equal to V divided by I. So this is resistor A, RA. Voltage is 20, and current is 20 times 10 to the negative 3. So this is going to be 1000 ohms. All right, that is the resistance for the first one. How about the second one? Again, you will apply the same exact concept. So we're going to just take 2 points on this, a point on this line, so we can determine the coordinates. So this is the point we took. What is the voltage? The current value first, it's 5. So I is equal to 5 milliamperes because this is in milliamperes. And the voltage is 16. Again, we need to convert this to amperes. So it's 5 times 10 to the negative 3 amperes. So 16 volts. So now that we have this in amperes, again, RB is going to be V over I, which is 16 divided by 5 times 10 to the negative 3, which is equal to 3,200 ohms. All right? And that's how you would solve such a question. And that's pretty much it for V is equal to IR. Anyone has any questions about this before I move on to power and all of that? I'm just trying to see if there's any other question that can be asked. That's pretty much it. What about from here? All right. Before I move on, since there's no questions, let's take a 10-minute break, okay? And then we will go into power energy and building a circuit and understanding how to solve for a circuit and all of that. I hope that the concepts are clear so far. Let me know if you have any questions. I will be around. I will be here. Just let's take a 10-minute break. We'll be back at 8:10 p.m. All right? Take a 10-minute break and then we will go look at power and energy when it comes to electrical systems and building a circuit and what the symbols of a circuit means and all of that. All right, if you have any questions, feel free to ask right now. I will be around. Okay, so let us talk about power. Okay, I'll actually make a new page for this. So power, just a second, power. We know that power is simply work or energy over time. Okay, I'm just going to do the quick derivation of how you can apply this for, you don't need to memorize the derivation. I'm just going to show you guys so you guys can have a better understanding. But generally, it's work over time for any system. And in the case of electrical systems, work done, all right, is the amount of coulombs, which is Q, the charge, times the potential difference. You don't need to remember this, all right? If we plug this in back into the power, it is QV over time. We also know that I is equal to, or I should say Q, is equal to the charge Q. We already defined it. It's equal to I times T, right? So we can plug this in back into the equation. We're going to get power is equal to I T V over T. If you notice, now we can cancel the time and we can get this new equation where power is equal to I times V. Again, this is just the derivation. It's not important. The most important thing is this equation here at the end, all right? Where power, if you remember, the unit for power was watts, the unit for current is amperes, and the unit for voltage or potential difference is volts, okay? This is how you will determine the power for any type of electric circuit in any case. As long as you have current and voltage, you can find the power either supplied or being absorbed. Obviously, this is just one form of the equation. There are different forms as well for this equation. So how do we know the different forms? If you remember our nice Ohm's law triangle, we had V, R, and I. Okay, so we also know that. So if we look at V, for example, we know that V is equal to R times I. So if we plug this back into the power equation, power is going to be equal to I times Ri, or in other words, power is equal to I squared times R. So we can find, depending on the resistance if given, the power being absorbed by that resistor using this equation over here, which is simply just a different form of the original equation, which is power is equal to current times voltage, using substitution. Another way of substituting, you can say that I is equal to V over R, all right, V over R using this. So I is going to be equal to V divided by R. Again, if we substitute this back into the original equation for I, we're going to get V divided by R times V. In other words, power is also equal to V squared divided by R. Okay, so this is just another equation that can be used. These are all the exact same equation, the same exact power equation that is used for uh, electrical systems, I should say. And then, and you can find the power in watts of any circuit by applying depending on what you are given in your question. All right. So let's start off with a very simple question. Let's say that we are given this problem over here. So 100 watt electric light bulb, 100 watt. Again, 100 watt means power. P is given to be equal to 100 watts. And then is connected to a 250 volt supply. So our voltage is 250 volts, right? Determine part A. They want us to find the current flowing through the bulb. They want us to find I. Remember, P is equal to I times V. If we rearrange this, you can say that V or I is equal to P divided by V, if you just divide V in both sides. Another way, if it makes it easier for you guys can also draw the power triangle, which is the exact same idea. At the top, it's going to be power. At the bottom is going to be current and voltage. So if you want to find current, it is power divided by voltage. If you want to find voltage, it's power divided by current. And if you want to find power, in this case, it's going to be I times V, which is our general equation. Okay? So now since we are trying to find current, I is equal to, first let's look at the units. The unit is watts for power, correct, and V for voltage, correct. So we could just plug this into this equation. And it is going to be 100 divided by 250, which is 0.4 amperes. Part B. So now we have found our current. Part B says find the resistance, R. Again, we can use now Ohm's law. All right, since we have the voltage given in the question and we have determined our current, we can straight up find our resistance given using Ohm's law. So we know that R is equal to V over I using Ohm's law's triangle. So again, units are all correct. So we can just plug in 250 volts divided by 0.4 amperes, which is 625 ohms. This is how a question might come when it is relating to power, if you're given power and how to determine it. Let's look at another question. So another question says, right here, problem 10, it says that calculate the power dissipated when a current of 4 milliamps, so they want us to find power dissipated. I'm going to explain, after I solve this question, I'll explain what they mean by power dissipated in a minute. But it's simply just power, so you want to find P. This is what we're trying to find. When a current of 4 milliamperes, which is I, so it's given in 4 milliamperes, convert this directly into amperes, so it's 4 times 10 to the negative 3 amperes, all right? Flows through a resistance of 5 kilo ohms. So we have R is equal to 4 kilo ohms. Again, convert this into ohms, which is times 1,000, so it's equal to 4,000 ohms, all right? So now if you notice, we are given current and resistance. There's two ways of solving this. You can, one, apply this equation directly over here that we determined earlier, which is P is equal to I squared R, through memorizing, through whichever way you want, or you can first apply Ohm's law to find voltage. So voltage is equal to resistance times current, which is equal to 4,000 times 4 times 10 to the negative, sorry, it is 5 kilo ohms, not 4. 5 kilo ohms. So this is 5 kilo ohms, so it's 5 times 1,000, which is 5,000. So 5,000 times 4 times 10 to the negative 3, which is the current. And now we have determined our voltage to be 20 volts. Yes, 20 volts. All right. Now that we found our voltage, all right, so this is our voltage V. All right, so this is voltage V is equal to 20 volts. We can simply apply P is equal to I times V, which is, what is the current given? 4 times 10 to the negative 3 times the voltage, which is 20 volts. And this will give us that power is equal to 0.08 watts. All right, the unit for power is watts. And this is how you would solve it. So remember, you can always use Ohm's law to determine your voltage given the other two, or the resistance given the other two, or your current given the other two. And then you can plug it into back the power equation, which is simply I times V, to find out what your power dissipated in this case is. So one quick thing. So we have power supplied and power dissipated. This is just a little bit of theory, right? It's good to know. It's good to understand, because later on you're going to be applying this a lot later on in your next years of your studies. So power supplied is basically when you have a supply, a battery, for example. Let's say we have a battery here. So this battery is providing power if it's connected to something. This is basically called the power supplied. And then if you say we have a resistor here, or a component, this is absorbing power, or it's dissipating the power. This is what is meant by dissipated power. It is the power that is going into something, and it is absorbing it, or using it, or letting go of it, or burning it, or whatever. Yani it is the thing that is receiving the power itself. That is the idea of dissipated power. All right, just a little bit of theory, nothing too confusing. And that's pretty much it for power. The remaining questions are very similar. I want to just move on to electrical energy. So again, remember when I said in the derivation here. So remember that power is work or energy over time. All right. So if you want to find electrical energy at any time, all right, if a question is ever asking for electrical energy, this is simply just E or W, the work done or the energy. This energy, remember that power is equal to energy over time. Therefore, you can say that energy is simply power times time. Again, energy is always in joules, power is in watts, and the time in seconds. This is how you can find your electrical energy if the questions ever ask for electrical energy. All right. That's pretty much it when it comes to electrical energy. There's another unit that is sometimes used for power. So we know that power is in watts, right? Power, the unit of it is watts. All right. Sometimes power can be given in, or sometimes you hear the saying horsepower. What is horsepower? Horsepower is basically just a unit, all right? So it's also power, but it is a different unit, all right? This horsepower, 1 horsepower, which is sometimes given as HP, is equal to 746 watts. Okay, so this is just another conversion rate. Yani this is just converting the unit from watts to horsepower. You're going to be using this conversion. For example, let's say we are given power is equal to 20 watts. All right, to find this in horsepower, if you're using the method I taught you, it's going to be very simple. You just put watts at the bottom because that's what we are trying to cancel. And we are trying to find horsepower, so we're going to put that at the top. Okay, so this is just a unit, all right? Remember, this is just a unit. So we know that 1 horsepower is 746 watts. So now the watts will cancel, and you're going to get your value, which is 20 divided by 746 horsepower. Put that into the calculator and you will find a value in horsepower. Let me do that really quickly. 746, which is 0.0268 horsepower. Okay. So this is just a different unit. Horsepower is just a unit, nothing to be confused about. Most of the time, so this is a more closer value. Most of the time they say 1 horsepower is equal to 750 watts, just because it makes the calculation much more easier. In the exam or in any test you are given, they will mention how much is 1 horsepower or how much you should consider horsepower. Same as gravity before, they tell you it's 9.81. Similarly, here they're going to tell you what to assume the horsepower rating is. All right. This way, you will always just be able to apply this equation no matter the power given. And the opposite, yani vice versa, you can also do it. So let's say you have 150 horsepower, right? If you want to convert this into watts, you're going to multiply. At the bottom, you're going to put horsepower. That's what you're trying to cancel. And at the top, you're going to put watts. So 1 horsepower at the bottom, 750 watts at the top, because 1 horsepower is equal to 750 watts. So horsepower and horsepower will cancel. In watts, this is going to be 150 times 750 watts. So it is going to be a large number of 112,500 watts, or in other words, you can say this is 112.5 kilowatts. All right, again, just conversion of units, same exact method that we did up here. All right, so let's see if there's any other question about this. All right, let's do this question. This is a good question. Problem 14. So let's say we have a 12-volt battery, which is connected across a load having a resistance. So let's go step by step. We have 12 volts. So this is our voltage. 12 volts, all right, is connected to across a load of having resistance of 40 ohms. So our resistor is 40 ohms. Before even reading the question, we know we can find current, we know we can find the power, all of that because we have two of the unknowns and we can just plug into equations. So let's see what the question wants. So it says determine the current flowing in the load. That's the first thing we need to find, current flowing. The power consumed, that's the second thing, power consumed. So the first thing they want us to find is current. Let's find that. So if we are using the equation, the triangle, so it's equal to V divided by R, which is 12 divided by 40 since the units are correct. So it is equal to 0.3 amperes. Done with the first part. The second part B says, actually, let's change the color. So the second part says the power consumed. All right. So power consumed, part B, is power. Power is equal to I times V. We have our current. We found it from the previous question. Times, we have our voltage given in the question here, which is 12. So 0.3 times 12, this is going to give me 3.6 watts. And now we have found our power. And let's look at the last part. It says the energy dissipated in 2 minutes. All right. So what does this mean? Remember what energy was? Energy was simply power times time. All right. So first of all, it was given time is 2 minutes. First thing we do is convert this into seconds. All right. So minutes at the bottom, seconds at the top. 60 seconds is in 1 minute. The minutes will cancel. This is 20 times 60. Oh, sorry, 2 times 60, which is going to be 120 seconds. This is the first step. Remember, the trick here is always conversion of units. This is where people will make mistakes, not applying the questions, but the conversion of units. Now, they are asking for energy dissipated, E. We know that E is equal to power times time. We found our power earlier to be 3.6 watts, and our time is 120 seconds. So our energy dissipated is going to be 432 joules. All right, because energy is in joules. Energy, which is basically watt second, this is the same thing as joules. All right, so joules is equal to watt second. Okay. Very straightforward, very simple, nothing to be confused about. It's just application of equations. I'm pretty sure most of these equations will be given. Double check with your tutor, see which equations you guys might need to memorize, or if they're going to give you everything. They might not give you Ohm's law because Ohm's law is a very important theory or something that you need to know by heart. But again, double check with your tutors, see if you get a formula sheet to know what you will be given or not. Yeah, that's pretty much it for energy. Let me talk now a bit about definitions and theories. So earlier we were talking about, actually, let us go directly into circuits, all right? So, and I'll explain definitions as I go. So first of all, this is what a normal circuit would look like. So you'll have something like this, all right? Let me actually draw it a bit more neatly. So you're gonna have something like this. You might have a resistor over here. Okay. This is what a circuit might look like, a very, very basic circuit, all right? So these are the two most important symbols you guys need to know. So the first one is this one. This is a cell, all right? Or you could say it's a battery, but it's technically just one cell of a battery, all right? This provides voltage and current for the entire circuit. So what does that mean? If you notice, first of all, the symbol, one of the sides is longer than the other. This side is your positive side, and this side is your negative side. You don't need to know much more about it than that for now, but this is what they call the polarity of the cell. You're going to have the longer cell, which is always the positive, and the smaller, which is the negative, all right? And usually in a question, you will be given a voltage for it. So let's say, for example, 12 volts, all right? And I'll talk about that in a bit. But this is what it usually looks like. And this is a resistor on the right side over here. This over here, this is a resistor. Okay. And usually in the question, they will give you like something like, I don't know, 50 ohms or something like that. Okay. So this is what it would look like as a, this is the symbol for it, I mean, when you draw it into a circuit diagram. So this is what a basic circuit diagram looks like, okay? So this is the resistor, the symbol for it. The resistor is in ohms. This is your battery. Your battery supplies current and voltage, and the voltage here is given. Usually the voltage is given. And current, remember current, which is I, is always flowing from the positive, like this, of the battery back to the negative. All right? So this orange thing, this is I, or your current. Okay? So current is flowing through these wires, okay? From the battery, it's going to the resistor and then coming back to the battery. And this is how a circuit works. A few rules about a circuit: it has to always be closed. يعني لازم يبدأ من البطارية ويتخلص على البطارية, or else there is no current flowing. All right. So again, the circuit has to be closed. So it has to start from the positive into the negative, or else you will not have any current flowing through it. Now, if you want to apply any of your laws here, very simply, all you can do is apply them directly. So for example, we are not given the current here, but we can find it. How can we find it? Using Ohm's law. All right. So let's say we have, we're given the voltage is 12 volts, or it's actually the EMF, which I will talk about after this, solving this. All right. Which is also the voltage. It's the same thing, 12 volts. And we have our resistance R, which is given to us as 50 ohms. How can we find current? Current is equal to V divided by R, which is 12 divided by 50, which is going to be 0.24 amperes. All right. So we can find our current very simply this way. Okay. This is what this means. This is how you look at the circuit and you understand how to apply the rules. All right. So you are given a voltage. This voltage is going through all of this. And you have a resistor. This is the resistance of the circuit. Okay. And or this is the resistance of the resistor, I mean, sorry. And there's going to be current that is flowing through. This current you can find using Ohm's law. Now, how can we find the power supplied by this battery, or this supplier, or the cell, I should say? Again, same idea. Power is equal to the current times the voltage. The current that is flowing through the cell, we have found it to be equal to 0.24 times the voltage of the battery, which was 12 volts. All right. So the power is going to be 2.88 watts. All right. This is how you apply it. So this is a basic circuit diagram. This is what it looks like. Again, I repeat, this is the cell, or it's a single part of the battery, basically. And it provides voltage. This is the symbol for a resistor. And then there's going to be current flowing from the positive to the negative side of the battery always. All right. When you have a single battery, that is. So I keep saying battery, even though this is a cell. This is technically a cell, but a battery would be a group of cells. So if you want to draw it in a circuit, this is what a battery would look like. Right? So they're going to draw multiple cells in a row, and then they're going to give it a value of 50 volts. Right? So I said something about electromotive force, all right, which is EMF. So I said this is the EMF of the battery. All right. Again, EMF is just voltage, but it is also known as the EMF is electromotive force. All right. So the electromotive force, what it is basically the energy or the voltage provided by a source. All right. This is all that this is. It is just the voltage when it is being provided by a source. This is what they call as electromotive force. Obviously, there's a lot of more theory about it because of the technicalities of what's happening inside, but I'm not going to bother you with all that theory. What you guys need to know is if you read EMF, just know that it's talking about the voltage provided by the source. So it's basically the voltage of a battery source or of a cell. All right. This is basically a source of voltage, all right? That's why I call it a source. So they call it a voltage source. It can be either a battery, a cell, a power supply, whatever it is. But most of the time, you guys are going to be seeing it in this form as either a battery or as a singular cell like this. And that is pretty much it. I'm trying to think if there's anything else from basic circuits that you guys might need to know. Nope, that's pretty much it. Yeah, this is the whole idea of a basic circuit. So you guys now understand how the current is flowing. Again, it's always going exiting the positive of the battery and entering the negative. And that's, yeah, pretty much it. All right. Any questions about this? Any questions about what I've covered so far in general? While I look for any other questions I might use. Okay. Then let us keep going on with some more, a bit more, they're not that complicated, but a bit more challenging, I would say, uh, power questions. Again, if you apply the theory, you apply it directly, everything is going to be very easy. If you just understand everything I've done today, you're going to be very well, like comfortable with any electrical question in general, whether it's asking for power, voltage, current, or resistance, you will be able to do it. So here, electrical equipment in an office takes current of 13 amps. So we have our current, which is 13 amperes, from a voltage supply of 240 volts. So 240 volts. Units are fine. And we are given I and V. We know we can find power. We can find our resistance if there is any. We can find all of that. The question says, estimate the cost per week of electricity if the equipment is used 30 hours each week. All right. And 1 kilowatt hour of energy costs 12.5 pennies. And this is a very important thing. So we need to find cost per week. All right. So we need cost per week. Okay. We know that the equipment is being used 30 hours over the whole week. Right? So we know that the equipment is being used for 30 full hours for one whole week. All right? So in other words, we can say our time is 30 hours. First thing we do is we convert this 30 hours. Actually, we don't need to convert it into 30 hours, and I'll explain why in a bit. Let's keep it the way it is. When it comes to cost, usually you will not change it, and I'll explain why. And it's also mentioned in the question. And 1 kilowatt of energy. So 1 kilowatt of energy, 1 kilowatt hour of energy. Notice here it's given in hours already of energy. Costs 12.5 pennies. Okay? Well, it's 12.5 pennies. Penny اللي هو الفلس يعني. Okay? So first things first, what do we need to know? We need to find the cost of energy. This is what they want us to find, the cost of energy. How can we find energy? We know the equation for it. So energy is equal to power times time. We also know that power is equal to I times V, which we can find directly right now. So power is 13 times 240. So power is equal to 13 times 240 is 3120 watts. All right. So this is the power given in watts. Now we need to do power times time. All right. So energy is going to be power, which is 3120 times, again, I am keeping this in hours. Why am I keeping this 30 in hours? So this is in watts and this is in hours. So the energy, total energy being used is equal to 3120 times 30. That is 3120 times 30, which is 93600 watt hour. All right, or watt hour. The reason here is because I am not writing this in joules anymore. I'm not writing the energy in joules. I am writing it in watt hour. So if you notice, I am writing this in watt hour. This is not equal to joules, all right? It's not the same. Why am I doing it this way? Because they gave us the cost for 1 kilowatt hour. So we need to find out the same unit here so we can find the cost later on in pennies. So how do we do that? Here we found our value for energy in watt hour. We need to convert this into kilowatt hour. So in other words, we need to do 93600 watt hour times watt hour. That's what we need to cancel, kilowatt hour. So 1 kilo is 1000, right? Then doesn't matter what it is, watt hour, pineapples, whatever. 1 kilo is 1000 times of whatever the unit is. So watt hour and watt hour. So here the watt hour is going to cancel. We're going to have 93600 divided by 1000 kilowatt hour. This is the energy that is being used. So if we simplify this, the energy now in kilowatt hour is going to be 93.6 kilowatt hour. Okay? This is the total energy that is being used. So we know that one of those energy, and one part of that energy, 1 kilowatt hour, is going to cost us 12.5p. I'm going to just write that again here. So 1 kilowatt hour is going to give us 12.5p. 2 kilowatt hour, what are we going to do? إذا استخدمنا اثنين منها, we're going to be multiplying by 2, right? 12.5. If we have 3 kilowatt hour, we're going to be multiplying by 3, right? Think of it يعني as if these are water bottles. The one water bottle costs 12.5. 2 water bottles will cost 2 times 12.5. Same idea, same concept. So what if we have 93.6? So 93.6 kilowatt hour is going to be 93.6 times 12.5 pennies. All right? So when we are going to multiply this, we're going to get 93.6 times 12.5. This is going to give us 1170 pennies per week. So this is the amount it will cost them every week if they're running their machine, whatever machine, their equipment يعني, for 30 hours in the week. All right. If you want, you can also convert this to pounds, but it doesn't really matter. زين. to pounds like this 11.70 pounds لأن 100 pennies is 1 pound. يعني كأنه من فلس إلى ربابي إلى ربية كم ربية كذي. تمام. What is the EMF law? There is no EMF law. Okay, so going back to electromotive force, there is no law for electromotive force. Electromotive force is simply just voltage, all right? So this is just voltage. It's the same laws that you are using for voltage for in any case. It is the same thing, all right? So it's just equal to voltage. It's just a different wording when they are talking about the supplied voltage. That's it. That's what electromotive force is. So there's no specific law combined with EMF. All right. And that's it for solving this question. All the other questions are exactly the same, very similar to what I've been doing. Let's do one more with cost so that you guys can get the better idea of it. And we will conclude it here. All right. Determine the power dissipated by the element of an electric. So first things first, what are they asking for? Power dissipated. معناتها we need to find P. All right. By the element of an electric fire resistant 20 ohms. So we know that our resistance R is equal to 20 ohms. When a current of 10 amperes flow through it. So we know that our current is 10 amperes. Now, obviously, we can determine this directly here. So first things first, before even continuing with the question, we want to find power dissipated. How do we do that? Simple. First, we can apply our Ohm's law. We know that V is equal to R times I اللي هو 20 times 10, since the units are all correct and in standard form. So this is going to be 200 volts. So we found our voltage. Now to find power, it is current times voltage, which is 10 times 200. So it is 2000 watts, or you can say 2 kilowatts. All right. Then 1000 watts is 1 kilowatt is 1000 watts. For 2000 watts is 2 kilowatts. All right. Let's see what the question says. If the fire is on for 6 hours, all right, معناته electric fire of resistance, electric fire is consistently on for 6 hours. Determine the energy used and the cost if 1 unit of electricity costs 13 pennies. Okay, 1 unit of electricity is 1 kilowatt hour. All right, this is the standard when it comes to the cost and to the determination of energy usage. When we're talking about energy usage, usually they write it as in kilowatt hour rather than in joules. It's just a standard that has been established from a long time ago. So 1 unit is equal to 1 kilowatt, and we know that 1 kilowatt hour is 13 pennies. So if the fire is on for 6 hours, so we know the time is 6 hours, which is, if we want to convert into seconds, oh, no need, actually. In this case, because we want to find our final answer in kilowatt hour, so we don't have to convert this into anything, all right? We have our power, we found it in kilowatts as well, so we can use it in kilowatts, all right? So we have our power in kilowatts, and we have this in hours. So we know that energy is equal to power times time. Since this is already in kilowatts, let's keep it in kilowatts. So 2 kilowatts times 6 hours. Because if you multiply this directly, you're going to get 12 kilowatt hour, which is the unit that we want. All right, this is the unit that we want because that's what we are trying to find. When it's relating to cost, most of the time it is going to be given in kilowatt hour. All right. So we saw earlier that 1 kilowatt hour costs 13 pennies. So 12 kilowatt hours will cost 12 times 13 pennies, which is 156 pennies, or 1.56 British pounds. All right, this is how you would solve it if you have costs that are being added to the questions. Very straightforward, very easy. Nothing more to it. The last concept that I can go over very quickly again is efficiency. So efficiency is usually given by this symbol. All right, it's this symbol which looks like the letter N. This is known as efficiency. زين, efficiency عادة when we talk about something being efficient يعني how good it is, يعني how proper is it, how much يعني are we benefiting from it. زين, how efficient are you. مثلا يقولون are you efficient when you are studying, معناته are you studying all the concepts you are supposed to, are you using up your time properly, are your يعني fees going into something useful. That's the idea. Are you efficient with your money, are you not spending unwisely, is it all being utilized properly. This is what efficiency is. So efficiency, when it comes to electrical systems or generally any system, it is always going to be, when it comes to power, I should say, power output divided by power input. Right? بما معناه, we want to know how much power is being received from the end of the system compared to how much power is being transferred to it. And the easiest way to think of this is when you're thinking of a motor. A motor يعني موتور بشكل عام عندكم يكون موصل في كهرباء. ففي هالكهرباء يكون في energy in this electrical circuit or whatever, a battery or whatever it's powering the motor. It has electrical energy. So this electrical energy, so a motor, زين, you're going to have an input to it. Okay, if I want to draw a quick diagram of it, a motor, زين, that is rotating. Okay, This is usually connected to a source, a battery or something. Then, so this is providing energy. This is providing electrical energy, which the motor then converts into mechanical energy, all right? But there is an output from this, which is being rotated, all right? Which is also consuming this energy. Tamam? Obviously, in reality, you will never have 100% efficiency. There will always be loss of power due to friction, due to improper system connections, due to a lot of other reasons as well. There will always be loss due to heat, due to light, due to a lot of things. There will be a loss of energy. But we know that there is an input energy, power input, and there is an output energy, power output, right? So how do we find the efficiency? So let's say this input. So usually for electrical energy, we're talking about watts. So let's say this is 1.8 kilowatts. Okay, so this is your power input. And when we're talking about motors, we are talking in horsepower. So let's say power output is 2 horsepower. All right. So now we have our output of 2 horsepower with an input of 1.8 kilowatts. We want to determine efficiency. First things first, we need to convert this into watts. So since we have, so let's call this PI is equal to 1.8 kilowatts and PO is equal to 2 horsepower. We need to convert this into watts. So we're going to put HP down and watts up. We know that 1 HP is 750 watts, all right? So this is going to be equal to 1,500 watts, all right? HP and HP will cancel, 2 times 750. Oops, this is the times. This will cancel. 1,500 watts. Same thing with PI. Let's convert it to watts. So this is 1.8 times 1,000 watts, which is equal to 1,800 watts, right? So now, what was our equation to determine efficiency? If we want to find the efficiency of this system, it's power output over power input, of course, times 100. I forgot because it's a percentage, all right? So times 100. So it is going to be efficiency is power output over power input times 100, which is equal to 1,500 divided by 1,800 times 100, and this is going to give you 83.33%. And this is how efficient our system is. It will never reach 100 because we will never get an output energy equal to our input energy in real life examples. And theoretical, of course, it is achievable because it's all theory, but in reality, there's always going to be losses due to whatever reason. Okay. Let's solve one more example of this. So this is the question that is given. A generator receives 7 HP, right, and supplies 20 amperes at 220 volts. So it is very important to understand what is your input and what is your output. It says receives 7 horsepower. So now this is your input. So input is equal to 7 HP, and it supplies. Supplies means it gives, so it's leaving it. It supplies output is 20 amperes. So this is I, which is equal to 20 amperes, and voltage, which is 220 volts. Notice here, they did not give you power directly. They want us to find the power supplied and of the generator and its efficiency. So first things first, we need to find the power supplied, which is simply the power output as well. So PO, power output, is going to be current times voltage, which we already know. So it's 20 times 220 volts. So the power output is equal to 20 times 4400 watts. All right, 4,400 watts. Again, same thing. Input, now we need to find it in, so PI equals 7 HP times, we need to find it in watts. So at the bottom, we're going to put HP. At the top, we're going to be putting watts. We know that 750 watts is 1 horsepower. Horsepower and horsepower cancels. PI is equal to 7 times 750 watts. So PI is equal to 5,250 watts. And that's it. Now you can find efficiency. You have P output and P input. Efficiency is equal to out over N times 100, which is 4400 over 5250 times 100, which is equal to 83.83%. All right. Is that correct? Wait 1 second. It's 81%, sorry. 83.81%. Okay. And that's it. That's how you can find efficiency for any question. Remember that this is a percentage. I hope this clarified energy in general and electrical energy and current, resistance, voltage, what they mean by potential difference. Potential difference is simply just voltage between 2 points or just voltage. And EMF, as well as how to build a normal circuit. So if we just do a very quick recap of what we did today. So we started with the very basics of power and energy. Remember the units. Remember, units have to be in SI, meaning current has to be always in amperes, length meters, mass in kilograms, and time in seconds. Remember your prefixes and how to be able to convert your units. This is the most important part of this entire concept as a whole, because if you make a mistake here, it doesn't matter how many equations you know, it doesn't matter how well you understand electrical components. If you don't know how to do this basic math here to convert, everything will become wrong. So current is simply just the flow of electricity in some way, or of the flow of electrons. Current, you can find the charge, which is basically how much current is moving through a specific place at a specific time by just multiplying current with time. All right, that is your charge. We also looked over resistance, what it means, and we compared it to an actual physical system. All right, resistance, basically high resistance means it constricts, it slows down the flow, it slows it down, it tries to stop the flow. And then we talked about voltage. Voltage is similar to height, how high up something is, and that's also known as potential difference. And then we looked at Ohm's law, which relates all these three together. R is equal to V over I, or V is equal to Ri, or I is equal to V over R. You can always use the triangle method to simplify it. We also looked at conductance, which is just the opposite, or the inverse, I should say, of resistance. Okay. Then we did some questions about all of these, and then we looked at how to plot and how to read the plot for current versus voltage. All right, remember the slope is conductance. And if you want to find the resistance, it's very simple. You just take any 2 points along this line because it's a straight line. So any 2 points are going to always give you the value of the resistance as it is for that resistor. And that's pretty much it for the first part. Then we talked about power. Remember that power is I times V. Again, you can always use Ohm's law with this equation. You substitute an I in place of or the V in place of here, so that you can find it in terms of resistance as well. Or you could just apply Ohm's law first and then just apply P equal IV to determine whatever you want. We solved a few questions about that. Just remember, power supplied is coming from a battery. Power dissipated is being absorbed or being used by a resistor or any system. Electrical energy is basically just power times time, just like we did before when it came to mechanical systems. So it's just power times time. And when we are talking about cost, sometimes we're not going to be talking about joules. Sometimes we might be talking about kilowatt hour. All right, that means this unit has to be in kilowatts and this unit has to be in hours. All right, this is when usually dealing with costs of energy. All right, so this is just a different unit, different standard. All right, this is not a standard unit notation, but can be used to solve questions as well. more related to cost. We looked at horsepower, which is basically 750 watts. It is just a different unit, and you see how to convert it. It's very straightforward, and that is pretty much it. And then we looked at what a cell is and what a basic circuit looks like, what EMF is, which is the electromotive force, which is simply just the voltage being supplied by a cell or a battery. A battery is just going to be multiple cells next to each other. All right, so this is just a battery. All right. We saw how a resistor looks like. So again, a resistor just is zigzags like this. This is just the symbol for a resistor. All right. And it can be anywhere in the circuit. I showed you how to apply Ohm's law and power when you have a circuit. Remember that current is always leaving the positive end, which is the longer side of the cell, and entering the negative end, which is the shorter side of the cell. And that is pretty much it. Then we talked about efficiency. Efficiency is simply output power over the input power times 100. I hope this was clear and made it a bit easier for you guys when it came to electric power. If you guys have any questions in general, you can feel free to ask. And